This is the second video for our Physics 12 final exam review. This is the one where we're going to take a look at circular motion, or uniform circular motion, and also in this chapter we also looked at gravity. So uniform circular motion was new to us in Physics 12. The idea behind it was that the object, even though it was moving at a nice steady speed, because it was going in a circle, it was actually going to be accelerating. So that's kind of the key thing I'm going to put in right off the start here. For uniform circular motion, the object is always accelerating as it goes around the circle. Gonna skip my little table here for just a moment and jump down to underneath it. The direction for that acceleration for uniform circular motion, the way we talked about it in our classes, we said it was towards the center. There are going to be some forces that cause that to happen, but it is going to be towards the center. Worth pointing out, we saw this in one of our little responder questions, that towards the center is not a standard direction, but at any given time that would be the way that it's accelerating. Now the table up here, we've got some kind of multiple choice deals here where you pick whether it's constant or changing. There are 3 of them for talking about aspects of velocity and 2 for acceleration. And the reason why it's kind of asymmetric that way, and I've got 3 for velocity, bit of a, I don't know, is it a trick question? I don't know if you'd call it that or not. But these 2 things here, the size or magnitude of the velocity and the object's speed, those are the same thing. Just going to write that in. You'll hear it called either one of those, but you need to respect the fact that speed is really just nothing more than how big the velocity is. So for uniform circular motion, it's like you're in a car going around a circle and your cruise control is on. The speed of your car is constant. And again, exactly the same thing. The magnitude of your velocity, it's the same thing. That's constant. But velocity is better than just the size of the velocity. It's also the direction of the velocity, all packed into that one word, velocity. So velocity being a vector, because the direction is changing, the velocity is always changing for uniform circular motion. For the acceleration part of this table, the size of the acceleration, the magnitude of the acceleration, yeah, we've got a couple of neat little equations that let us figure out how big that size is. It's nice and stable. We could maybe go v squared divided by r, or maybe we're going to go 4 pi squared r all divided by t squared. Those show you what that constant value is for the size of the acceleration when you have uniform circular motion. So that, it's nice and stable. It's a constant thing. But acceleration, just like velocity, if you want to just talk about that generically, that is a vector. So it has its size and it has its direction, and that towards the center direction is continually revolving. It's always different moment to moment. So actually the acceleration technically is changing from moment to moment to moment. All right, theory's done, at least for a page or 2. Let's try a few of these questions out. Question number 1. Using a string that will break if the tension in that string exceeds 48 newtons, 3 kilogram mass is spun in a horizontal circle with a radius of 70 centimeters at ever-increasing speed. So it's just going faster and faster and faster. At what speed is that string going to break? Okay, so you want to start thinking about free body diagrams. And for this one, as that mass goes around and around and around, there's this rope creating a nice little tension in towards the center. Now, it doesn't mention anything about friction. It doesn't mention anything about slowing down at all. But, okay, let's be fair. I guess there would be like an mg going down here and some sort of Fn going up. But I actually don't even need to worry about those. In this particular question, we're not even wanting to talk about those. I'm just going to kind of scratch those out. And the only force that's going in the towards or away from the center direction is actually that rope tension. So I'm going to fire up the best equation ever. Good old F net equals ma. And when I stare at this question, it looks like the only force out there is tension, just how tight that rope is. And it's going to make that mass accelerate. And so back in chapter 2, when we would do these questions, we would look at that A and go, okay, it's got to be one choice or the other. What would be good here? They're asking you about speed, so I'm going to choose to put in the version that says v squared over r. And they want you to get up to that speed where the string, I guess, hits that tension of 48 and finally breaks. So it's just a case of plug and play now. Just dropping the numbers in. We've got a tension of 48. The mass is 3. We're looking for the velocity. and it's got a radius of, well, they said 70 centimeters. We're going to go 0.7 meters. Oh, and I almost made a mistake here. That v, it's got to be squared. So it's just a case of solving for v, taking a square root. I almost forgot to take a square root there. V squared, that's around 11.2. You take a square root. That velocity is, I think it's around 3.35 meters per second. So key things, we're going with F net equals ma. We're looking at the free body diagram to think about what the net force is going to be. And for the A, we're picking one of the two possibilities for A. Every single one of these is going to be like that. They get a little more challenging, but they all have that idea at their heart. This one is a merry-go-round question. Kids just standing there. Hopefully they've got some good shoes. Might be worth pointing out that, race cars, exactly the same as this story here. So I'm going to put race cars are similar. So we're reviewing race car questions at the same time. When that child is spinning around on the merry-go-round, there are some interesting forces acting on that child. The most interesting one, I think, is actually that force of friction on their shoes that's pulling them in towards the center. Without that force of friction on their shoes, there's no way they're going to actually stay there. There is an mg pulling them down towards the center of the earth, but that blue platter there is going to be pushing them back up, so there's going to be an Fn that's going to match that. So the Fn and the mg, they match each other, and they're not even really in the interesting direction. They're not in the towards the center or away from the center direction. So I'm going to go and jump into F net equals ma. I'm just going to throw it way over here. And let's see what this thing here says. I got a 40 kilogram child on the merry-go-round. It's going around with a period of 3 seconds. Oh, okay, so I might use that other version of A. The coefficient of, oh, that's interesting, an S there, of static friction is 0.64. What is the farthest that they can stand away from the center without slipping? Yeah, it gets more dangerous when you get away from the center. So I look at the picture and I go, yeah, there's really only one force going on this thing in and out of the center. It's force of friction, and it's towards the center. That is good news. Towards the center is positive. It's the way it actually accelerates. So I'm going to go force of friction is equal to mass times, now I'm going to pick a version of A, but I'm going to go with the one that's 4 pi squared r all over period squared. I have access to that one because they've given me the period. But I'm kind of stuck. I'm looking for the r, but I don't know the force of friction right now. But then I look at it and go, okay, well, hang on. On my formula sheet, I've got this equation. Force of friction is equal to mu times Fn. If you are doing a question where objects are sliding, if it's kinetic friction, oh, by all means, use the equation. Just swap out an FF with a mu Fn. But if you're doing one like this, where the kids' shoes are actually static, they're stuck, you can't always use this equation. There's a kind of a test you have to apply. For static stuff, you can only use this equation for static coefficients at the slipping point. So I'm going to leave a little note in there. Yeah, this is great, but only at the slipping point. But as I read this question, we are at the slipping point. It says, hey, keep working your way backwards, stand there for a bit, see if it works, until you get to the point where it slips. So, oh, this is good, right? It's going to be okay. We can swap out an FF and put a mu Fn in. And I'm going to do exactly that. In fact, hey, there's not a lot of room left here, so let's get right to business here. I'm going to put in that coefficient of static friction, and for the Fn, it's not like this kid's on a ramp or anything like that. They're just standing there on the ground, so I'm going to put in mg because it'll equal the value for Fn. So there's my force of friction. That's going to equal mass times 4 pi squared. I'm looking for r all over period squared. And actually, it's kind of nice. The mass in this story goes away. We don't even really need to know that they're a 40 kilogram kid. It's actually mass independent. And now it's just a case of plug and play. We'll throw the numbers in. We've got 0.64, got a 9.8, we've got 4 pi squared. There's your r that you're looking for, and a period of 3 squared. And when you're done, I think it's around 1.42 meters. 2 or 3 sig figs, throw some units on it, and we're done. All right, next one. Getting a little more interesting here now. We're going to go with a vertical circle. got a 6.1 kilogram object on the end of a connecting rod. The connecting rod doesn't have any mass, so you don't have to worry about that. And it's spinning around in uniform circular motion, so it's going at a nice, steady pace. Period of 0.8 seconds. That's how long it takes to go around. And you're asked to try to find the tension at the bottom. Hey, it's review. We're getting ready for the test. Let's talk about the top and the bottom. When you're at the top, the force is on you up at the top. You would have an mg going down. And if it was like a rope, it would definitely be pulling down. The rod, I guess it probably could push up, but I'm going to suggest that, you know, if you're actually going really fast, you might actually need to have the rod pulling down as well. So at the top, especially if this was a rope, you might see a picture kind of like this. We are down here at the bottom, going at a nice constant velocity. We do have an mg going down, but we want to make sure this thing accelerates towards the center. So this connecting rod is going to be under tension. It's going to be pulling up like crazy on that 6.1 kilogram mass with more than its weight to make sure that it accelerates towards the center. So I'm going to dive into F net equals ma. I'm going to stare at that picture. I'm looking at the bottom part of it. I'm going to stare at that picture with the object down there at the bottom of the circle and go, okay, what do we got? Well, I got two forces fighting each other. Tension's going one way, mg is going the other, and for circular questions, towards the center is positive. So I have a tension going towards the center minus an mg, and that's going to make that mass accelerate. So I got to go pick a version for A. Well, I'm going to go pick the version that has the period in it, because they've mentioned the period is 0.8 seconds. So I could put in here 4 pi squared r all over t squared. Now, I'm actually not even going to solve this question, because at this point it would be just plug and play where you're trying to find the tension. Instead, I'd rather point out a couple of things. I think it's probably a better use of our time than worrying about the numbers. You are looking for this value here. You're looking for this tension. That is a force. So when you're finished, you're going to say, hey, look, I've got it. The answer is in newtons. Allow me to apologize on behalf of all physicists for having an equation with 2 capital T's in it, and they're meaning different things. Over here, hopefully we can pick this up in context. This t is actually all about the period. It's all about how long it takes to go around exactly once. So that's measured in seconds. So 2 capital T's, but they mean different things. So that 0.8 goes in for that second one. For question number 4, I'm going to try to find the normal force, the force from the surface, from the seat of a roller coaster on a 50 kilogram rider. They're at the top of a vertical loop. Got a diameter that, ooh, that's not so good. Hey, you're writing the test and you see that. You see diameter, highlight that. You don't want to accidentally put 12 in. You want to put the radius in. And this roller coaster is going 15 meters per second. Okay, so we're doing a bit of a loop. Here's the top of the track right as we do the loop. And I'm just going to draw like a chair for the seat of the roller coaster. And you've got your rider in the roller coaster. They're having fun. And so they're sitting in there like this. They're upside down. And we have to think about what forces are actually acting on them. Well, there are 2. Gravity is pulling them down. And the seat is also pushing them down, right? So we've got them both. So there's an Fn going down also. So both forces are actually going down. But look, it's good. The center of the circle's down here. Towards the center is positive. Those are both positive forces for the way we do our physics. So we've got our free body diagram rolling. Now we can go into F net is equal to ma. Again, I look at that picture and I'm happy both those forces are positive because they're both down. So I have Fn plus mg is equal to m times, and then I go and I pick a version for A. I notice this speed here, so I'm going to go with the speed version, v squared divided by r. It is not mass independent. You cannot cancel the m's here. There's no m on that Fn term, so it's got to stay. That 50 kilograms is going in there. Looks like we have Fn plus 50 times 9.8 is equal to 50 times 15 squared. And again, this radius business, make sure you get a 6, not a 12. Highlight it when you're doing a test, right? So that when you go back and check your test, you can make sure you didn't miss it. So the Fn on this one, it ends up being well, it's like 1385. I'm going to call it 1390. That many newtons. So quite a bit more than their weight, actually. Their weight's 490, and there's even way more than that of compression force from the seat to get them to go around the corner. Hey, this one's quick. Just drawn a free body diagram for a person on that amusement park ride where they're kind of stuck up against the wall. There are 3 forces. The very, very good news is that the wall is going to push on their body. It's a surface force, so it's going to push this way. And that is an Fn, a normal force, right, a surface force. And also, that normal force now allows us to create some friction on their body. Friction's actually going to go that way. Good thing, because gravity's trying to pull them down. We've got an mg going this way. By the way, if you were going to do an F net equals ma calculation for this question, this force right here, Fn, this is your F net for this story. It's actually the normal force from the wall that's pushing them in towards the center. Okay, so these free body diagrams have been getting more and more interesting, and now we kind of get to the ultimate one here. We're going to do a kind of a Francesca-ish question, right, where we've got ropes that are at angles. This is the toy airplane one. So what does it say here? A small toy airplane is suspended as shown, flies in a nice little circular path. Yeah, okay, so there's actually like a radius down here, right? It goes in a circle down there. And first thing, just trying to find the free body diagram for that picture. Well, free body diagrams are all about real forces. What is actually out there acting on the airplane? I'm going to just redraw this airplane right here. There it is, coming at us. There are remarkably few forces acting on this airplane. In fact, there are only 2. There is an mg going straight down towards the center of the Earth, and the only other force that's acting on it in the plane that we can see is the rope, that tension in the rope, and it goes this way. It's a little stronger than mg. That's how all of those angled rope questions work. It's stronger so that if you think components, now I'm going to switch colors because it's not like I'm adding new forces. I'm just rethinking the tension one. If I rethink this tension one, I can say, yeah, this tension that's actually pulling diagonally, it has a vertical part to it, which is just as good as that mg. It's just balancing it out. And it's got a sideways part to it, a tx. And the tx does something interesting. Here, it makes that airplane go in a circle. And there's some sort of angle in there. Maybe we'll be able to find that angle in a minute. But the forces, really, there are just the 2 blue forces that are there, the T and the mg. So for me, I'd go with D. Right? It's got the tension, it's got the mg, and that's it. Don't go with B. I know, yeah, there's a net force towards the center, but option D has a net force towards the center. Once the Ty cancels out with the mg, then you've got a Tx towards the center, so it's totally fine. But now we're going to get into some calculations. So we're told some information here. The airplane has a mass of 1.8 kilograms. Okay, that's good. That'll let us figure out how big that mg is. It's going to be almost 18. The string's got a length of 2.5, and right now I'm not too sure why they're telling me that. And the string's tension is 23. Yeah, okay. So we jokingly call these Francesca questions because of that very first Francesca story back in Unit 1. Let's go and drop some numbers in here. This mg, if it's a 1.8 kilogram airplane, that makes the mg 17.64. And now you're telling me that this diagonal tension is pulling with 23. Okay, for all of these, again, we call them Francesca questions. The idea is somehow you've got to get to the point where you're comfortable talking about Tx. You can get there with Pythagoras, like some sort of x squared plus y squared equals z squared, or a squared plus b squared equals c squared, whatever you want to call it. Or you could do it with like SOHCAHTOA trigonometry, but somehow you've got to get to the Tx. I think on this one we can do it with Pythagoras. Because if that's 17.64 pulling down, then this Ty is 17.64. So this is actually a pretty easy deal to find out how big the Tx is. I'm going to go and do that right here. looks like tx, I really need that one, tx squared plus 17.64 squared is equal to 23 squared. In no time at all, I can come up with that tx, and it's around 14.75. That's my net force. I'm going to put that into F net equals ma. I'm also going to put that just back up in this picture here. So that is 14.75. Okay, great. Trying to find the speed of the airplane. That was what they wanted me to do. No problem. Here goes. F net equals ma. I've just found the F net. It's that tx. So tx is going to be m times, I got to pick a version here. I'm going v squared divided by r. I've got the tx. I am looking for that v, and at first glance it looks like this shouldn't be too much of a problem until I notice I don't have the r. But just dropping the numbers in, okay, I've got 14.75. They've told me the mass, 1.8. Looking for the v, good to see it there, and then, oh, the r. Oh, okay, no big deal. Let's just go back up to here. It's just a little grade 10 deal. We should be able to pull this off without too much trouble. This rope is 2.5 meters long. If we can just find some angle in there, if we can find out what that theta is, then we could do some SOHCAHTOA and get it to work. But wait, hey, that's the same theta as right here. So we should be able to find out this angle just based on these forces and then just steal that and take it over there. So that's what I'm going to do. Let's go and play with these numbers here and see what happens. I can work with any one of these that I want to. I'm going to go 17.64 and divide that by 23. That's going to be cosine, so uncos that. So we've got almost a 40-degree angle. So just from kind of looking at this here, looks like right in here, 39.9 degrees. That's the same as this one, 39.9 degrees. Yeah, okay, this question was a bit of work, but I think we're getting it. And sometimes you use that angle to do SOHCAHTOA to get the tx. We didn't. We did Pythagoras, but we're doing some trig here now to get the r. So it looks like for that r, got the hypotenuse, looking for an opposite side. Looks like sine of 39.9 is equal to r all over 2.5. Okay, so I'm going to go 2.5 sine of that answer. 1.6. So this thing is flying around with a radius of 1.60. Now we go to the bottom of the page, finish this off. Done. Only one thing missing. Don't forget to take a square root. 3.63. So key things. Free body diagram. It helps you out. If you've got one of these diagonal string deals, you got to use either Pythagoras or trigonometry to come up with the tx. Then the tx is going to go in for your F net. Last page for this one, just a little review of some theory here with gravity and how that comes in with orbits. Some of the stuff goes right back to Physics 11. If I've got a couple of planets, mass 1, and then another one over here, mass 2, and they're applying some force on each other, equal forces there. Hey, for force, the equation looks like this. I'm just going to kind of review all the different equations that you kind of see on your formula sheet there. So we've got the universal law of gravitation, that inverse square law. Now, when you've got things that are sitting on the Earth, if the Earth is your M1, and then you've got some other M2, like a person sitting up there, and you're curious to take a look at how much gravity force there is pulling down on that person, right? What's that force going to be there? Well, that person is 1 radius away from the center of the Earth, right? Let's find a color that'll show up here. They are 1 big Earth radius away. What we do in physics all the time is we say, hey, look, here's a quick way to get there. the force of gravity on that person is just mg. I guess it's like m2g, right? Because m1 is the Earth. And so this g, this little g here, it's this thing called gravitational field strength. That g, it's equal to everything that isn't m2 in this force equation. So it's the constant for gravity. It's a crazy looking g. Let's try that again. It's the constant for gravity, mass 1, all divided by the radius of the Earth squared. The units for this, there are two, I guess. Preferably, you'd want to say newtons per kilogram because it's warning you about newtons. Other people would say, well, yeah, because of F equals ma, it's equivalent to saying meters per second squared. You're right. It is equivalent to that. Okay, so now how does that gravity force show up when you go to do orbits? For orbits, if we assume it's a circular orbit for a moment, we've got this velocity that's tangent to the circle. The acceleration is caused by gravity force. The acceleration, just like the force, goes in towards the Earth. That's good. That's how circular motion works. And we can now go and see how F equals ma shows up in two different situations. So I'm going to put one F net equals ma over here, and another F net equals ma over here. The only force acting on that satellite is the force of gravity. So I've got big G, mass of the Earth, mass of the satellite, all divided by the radius of the circle squared. Okay, let's go talk about that here in a second. That's going to equal the circulating mass, which is the satellite, times, hey, let's try v squared over r. Now, before we go any further, let's go back to this picture, the r. The r goes from the circle to the middle of the circle. And the middle of the circle is right there in the middle of the Earth. So the r is this big dimension in there. But sometimes physics stories occasionally talk about this. They talk about the height of the orbit. Be careful. The height doesn't really fit into our physics equations. Radius does. So you might have to go and add on the radius of the Earth. But if they say, well, the orbital radius is this number, then they've given you the number I've drawn in green, and you're totally good to go. Okay, back to the left. The mass of the satellite goes away. It's independent of that. And you can rearrange this a little bit. You can cancel an r. You can take a square root. And a lot of people like to take this, kind of turn it into v for that satellite is equal to the square root of big G, mass of the Earth, all divided by the radius of the circle squared. All of that's under the root. The other option is to go gravity force is equal to the circulating mass, and then put in the period version of A, 4 pi squared r all over t squared. Now, the m2's cancel. That's about the only nice thing. And most physicists like to rearrange this until it looks like period squared, t squared, on top of orbital radius cubed is equal to another fraction over here, 4 pi squared all over big G, big M. Neither of these last two, that one or the one on the left, are on the formula sheet. You can create them as we did here in just a couple seconds, but it might be worth kind of knowing them when you walk into the final exam. Could save you a little bit of time. And here are a couple of questions that would use that. Number 7, Oberon is a moon on the planet Uranus. It has an orbital radius. Okay, that's good, right? Look, orbital radius. You don't have to add anything. That's good. Orbital radius, 5.83, 10 to the 8, great. And an orbital period, fantastic. And you're asked for the mass of the planet in the center that it's going around, the mass of Uranus. Okay, so if you had to, you could start again and go, oh, I've forgotten the formula. Great, start with F equals ma. In a little bit of time, you can get to here. T squared over r cubed is equal to 4 pi squared all over big G, I call it big M, right? That first mass, the mass of the thing in the center. If you're going to use that equation and you're going to try to find the mass, it's going to work. It's going to give you the mass. It's going to be in kilograms by the time you're done. But you have to make sure that you put seconds in for the period. So if it was given to you in days, you'd have to change it. And you have to put meters in for the orbital radius. So if they give it to you in kilometers, you'd have to change it. This one would be all ready to go, right? You could drop those numbers in and find out what the mass is. I'm not even going to worry about the actual answer. I don't actually have the number handy, don't even really care. Just pointing a couple things out. This m right here, it's sometimes called the mass of the central body. It's the big heavy thing in the center. It's the M1. Remember, mass 2 was the actual satellite. It doesn't matter at all. Okay, and M2 doesn't matter. It gets canceled in the equation, so its size is irrelevant to us. This other one uses the other option. Satellite travels around a planet at 9,000 meters per second, okay, 9 kilometers a second. Got, again, orbital radius. This is good news, right? Don't have to add anything. What would be the speed of a satellite with twice the mass? Oh, okay, twice as big of a satellite, orbiting at half that radius size for its orbit. Well, let's just kind of think about check scenarios here. If you get stuck, you can go back to F equals ma. A little bit of work, and suddenly you're here. V is equal to the square root of g m all over r. Again, this m, it's the central body. It's the planet the satellite's going around. And in this story, it doesn't sound like that's changing. It's not the mass of the satellite. So the mass of the satellite doesn't matter. You can go up to this story here where it says, what would be the speed of a satellite with twice the mass? Okay, so the satellite's twice as big. That part there, throw it away. It doesn't matter at all. It doesn't change the story. So if I was trying to do this, I'm just going to rewrite this where I've got a little room. I would go and do checks and arrows and start thinking about how this is going to play out with the value for V. Big G is a constant. It never changes. We're still going around the same planet, so you can put a check there. But we're going to go in an orbit size. Hopefully there's enough room to get closer to the planet. We're going to be twice as close to the center of the circle. So this r is going down by a factor of 2. And that means that the velocity goes up, but only by a bit. It doesn't double. It's going to go up by root 2. So I could figure out how fast this thing is going by just taking that old answer, 9,000 meters per second, just give it a little kick with root 2, and you'd have it. Last thing for this review, we did talk about Kepler's 3 laws of planetary motion. They were, first of all, that planets don't really have to go in circles. They can be a little elongated. They can be ellipses. And when it's farther from the central body, it's going slower. When it's closest to the central body, it's going faster. And that's what number 2 talks about. Just says that, yeah, the Earth, when it's farther from the sun, it's going at a slower speed. And if you were to connect the Earth and the sun with a line, watch it sweep out some area over maybe a month, you'd find it always would sweep out the same amount of area in a month. This last one, number 3, this is nothing more than F net equals ma. Just rearranged. Okay, we call it Kepler's 3rd law. And it's the mass of the central body that's in there, not the mass of the satellite. And that's the end of our second review.